Yes.
Oh, so let me start. Hello, I'm Sosuke Hosokawa, a master's course student at the University of Tokyo. Today, I'm going to introduce our work, efficient multi-GPU communication with NVSHMEM in Chapel. So first, let me talk about one of the current limitations in Chapel's GPU support right now. GPU in Chapel can't directly access memory on another GPU. For example, if we have GPU A and GPU B, a kernel running on GPU B cannot directly read or write to memory allocated on GPU A. In other words, GPU kernel can only access the memory on the device it runs on. This is one of the biggest bottlenecks when we try to enable inter-GPU communication in Chapel. In the current implementation, the only way for a GPU to access data on another GPU is through array-wise copying. This operation triggers data transfer using direct memory access for intranode communication, or GASNet via the CPU for internode communication, which means it doesn't use GPU direct RDMA. However, this approach has a few drawbacks. For small data transfers, the latency is quite high, and without GPU direct support, the internode bandwidth cannot be fully utilized for small data. Recently, a library called NVSHMEM has been getting attention for enabling PGAS-style inter-GPU communication. It's developed by NVIDIA, and it provides efficient communication between GPUs. Some of its features include device-initiated remote memory access, reduced communication overhead through technologies like GPU direct RDMA, and symmetric memory style PGAS API, similar to SHMEM, which the NVSHMEM's name comes from. So NVSHMEM essentially allows GPUs to directly perform one-sided operations like put and get from inside GPU kernel. So based on that idea, we thought, what if we could use NVSHMEM within Chapel? We started working on building a more efficient device-initiated inter-GPU communication library for Chapel using NVSHMEM. Of course, integrating NVSHMEM into Chapel is not straightforward. There are many challenges, both in the implementation and API design, that we need to address. To make NVSHMEM work with Chapel, we run into a few major challenges. The first one is building a proper pipeline to call CUDA device functions from Chapel using FFI. The second challenge is initializing the NVSHMEM runtime correctly within Chapel's GPU runtime. And finally, we need to design a user-friendly API so that Chapel programmers can easily use it. The first challenge is about the FFI for CUDA device functions. Currently, Chapel doesn't officially support calling device functions written in CUDA directly from Chapel. However, since NVSHMEM's device-side API is implemented as CUDA device functions, so we needed to make this work. So to solve this, we modified the Chapel compiler's CUDA build pipeline to support device function FFI. In particular, we added a GPU code linking step into the compilation pipeline inside Chapel compiler so that Chapel can link and call those CUDA device functions properly. Another big challenge is the runtime initialization of NVSHMEM. When we use NVSHMEM from outside of CUDA, in other words, from Chapel, the initialization becomes a bit tricky. To handle this, we extended Chapel's normal GPU runtime setup by adding two extra steps. The one is NVSHMEM module init function, and the other one is NVSHMEM init function. The first one, NVSHMEM module init, initializes NVSHMEM's internal handles using the CUDA runtime handle. Then, NVSHMEM init performs the main NVSHMEM setup, which includes the RDMA transport initialization for internode communication. And another important point is the design of the libraries API. Right now, our implementation simply exposes the low-level NVSHMEM API as it is. However, since this follows the SHMEM style symmetric memory model, it's not very user-friendly for Chapel programmers. We are planning to improve this part in the future, but for now, we are leaving it as future work. GPU-ready Chapel-style PGAS model like this code is ideal, but it is challenging to implement on top of symmetric memory-based PGAS of NVSHMEM. So next, let's talk about the evaluation of our library. As an initial evaluation, we conducted micro-benchmark to measure the bandwidth and latency of our implementation. For the experiments, we used the Miyabi nodes of the University of Tokyo's supercomputer. First, let's look at the bandwidth results. By using NVSHMEM's split function, we observed a significant improvement compared to Chapel's built-in copy operation. For small data transfers, like 4 kilobytes, the bandwidth improved about 100 times. And for larger data sizes, like 16 megabytes, we still saw about 3 times improvement over the original copy bandwidth. In addition, for large communication sizes, our implementation was able to reach the theoretical bandwidth limit of the interconnect around 25 gigabytes per second, which corresponds to 200 gigabit PS. Next, we evaluated the latency using ping-pong test based on atomic operations as shown here. And from the results, we confirmed that NVSHMEM on Chapel achieves almost the same latency as NVSHMEM running directly on CUDA, around 6.7 microseconds. When we compared it to the CPU-based OpenSHMEM implementation, the latency on Chapel was about 3 times slower, which is reasonable considering the difference in hardware and programming models. So to wrap things up, in this work, we explored the integration of NVSHMEM with Chapel to enable more efficient inter-GPU communication. Our current implementation already shows good performance in micro benchmarks, especially in terms of bandwidth and latency, which are comparable to native CUDA implementations. However, the API side still needs improvement. It's currently quite low level and not very convenient for Chapel users. As future work, we plan to improve the API design and further enhance the runtime so that Chapel's smart GPU support can become more efficient and user-friendly. That's it for my presentation.